Okay, sample 2. A boy standing on a 19-meter tall bridge sees a motorboat approaching the bridge at a constant speed when the boat is 27 meters from the bridge. The boy drops a stone to the water below. If the stone strikes the water 3 meters in front of the bow of the boat, at what speed is the boat traveling? So, if we draw ourselves a picture, there's two objects going on here. And so, I asked my class, what two objects are there? And they have the boat and the rock. Their motions are unrelated because we need to find the speed at which he's traveling. And we know that he travels a whole distance of 24 meters because he misses by 3 meters. The rock, on the other hand, is falling 19.6 meters. And so what actually ends this problem? Yeah, so the time is determined by the rock falling. The rock falling is what ends the problem. And so we can say that the rock falling in 19.6 meters, just like the previous problem, something falls in 19.6 meters in 2 seconds. And the way we do that is we've got our height, 19.6. We've got our VI of 0 and our acceleration of negative 9.8 meters per second squared. And so we can actually say x equals VIT plus 1/2 AT squared to get our t. Now, it might not be convenient because we have time in 2 places, but as you know, if VI is 0, it doesn't matter. And so we have 19.6, and that's it's falling, so technically it's starting up top and falling down, so it's a negative 19.6 equals 1/2 negative 9.8 t squared. We know that t equals 2. Mainly because the previous problem also had the 2-second problem, and that in that 2 seconds it will go 24 meters, and so 24 meters in 2 seconds, that's a distance divided by time to give us the speed of 12 meters per second forward. So really, we're just using the rock as a timing device to tell us when that boat has hit exactly 2 seconds. Now, if a stone is dropped in the water from a bridge 44 meters above the water, and another stone is thrown down vertically 1 second after the first was dropped, we have a rock and a rock, and this one goes down, 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 and the other one goes, well, it gets thrown faster, so really it just goes down, down, down. It's heading off with the initial velocity, and so we know that if we're dropping it from a height of 44 meters, that this rock will fall based on VI equaling 0 and A equaling negative 9.8 and our X falling, so negative 44 meters. And if we have VIT plus 1/2 AT squared, we know that our VI is 0. And we have X equals 1/2 negative 9.8. Sorry, our X is 44. So we have negative 44 equals negative 4.5 t squared. Well, honestly, we know that this is going to be about 3 seconds. I know that because of number 1, part A, but you could use a calculator. And both stones will drop and hit at the same time, so we actually need the initial velocity. We have the same equation, x equals VIT plus 1/2 AT squared, but in this time we have T2 is T1 minus 1. We're changing by 1 second. And so we have x, which is 44, same distance, equaling VI, what we're looking for. And instead of 3 seconds, we know this is 2 seconds, plus 1/2 negative 9.8 times 2 squared. And funny enough, we know that this side is going to be 2 squared is 4, divided in half is 2, negative 19.6. And on the other side, we have 2VI equals 44, negative 44. And so negative 44 plus 19.6, well, that's about 25-ish. Or 25 point meters per second. Then we check what direction is it going. Oh, that equals 2VI. But we can still add in a negative sign if we need to. And this item is going down. So then we divide it in half and we have 12.2 meters per second downward. We start to see that there's a trend here that we have two objects. We're actually doing a system of equations because T2 is T1 minus 1. We don't actually need to solve for the time. We could have left that in the formula. But it's actually easier to solve for the time in this case. And everything comes out normal.